Hi, Madhavi. So, hi guys. Today we are live with the purpose of actually working on the forecasting using an algorithm called decision trees. If you have remembered the previous session which we have conducted on logistic regression, so logistic regression is a classification algorithm. Means we have to classify a decision and we have to associate the decision with a probability. Similarly, today we are also working on a same kind of classification algorithm, but of course a different algorithm it is. Let's say decision trees. So decision trees is also a classification algorithm. So we're going to use decision trees to do the classification of a decision. So our objective is to understand whether what is the likelihood of stock out and stock overstock, right? So this is what we want to understand. Suppose in inventory, what happens when you're in supply chain and you need to check whether your SKU means stock keeping unit. It's a SKU is a stock keeping unit. You need to check whether your SKU is going to, meet the customer demand, or it will be excess inventory, because this is very important things in supply chain. So if you get stock out, it means you are going to lose the sales. There is chances of that you're going to have loss of sales. Means you're going to have a revenue loss. Why? Because suppose if you have a customer order, if you have a customer order of 100 units, and if your existing stock balance, is 5 units, right? So you are going, and customer wants the delivery immediately. Customer is not ready to wait for extra time for your sourcing or your shipment and production, then delivery. Customer is not ready to wait for that. So at this point of time, the shortage is equal to 95 units, right? So you're going to lose a sales of 95 units because customer is not ready to wait to to uh, to for the sourcing, because when you have shortage of the items like 95 units, right? It could be either you do not have raw materials, right? So what happens is if you do not have raw materials, then you have to give the order to supplier. Supplier will do the manufacturing. Then there is the inbound shipment, right? After inbound shipment, it comes to your factory. Again, again we will do the manufacturing, then do the shipment. That's the outbound shipment, right? So if you don't have raw materials, so the value chain is going to pass this through layers, and this will take some time because it's not going to happen immediately, because supplier also has to source the raw materials. If he doesn't have the raw materials, he will also source from her supplier, right? So this is a problem over here. So this is the supply chain or the value chain is not ready to serve the customer immediately, and customer is not ready to wait. So in that case, we're going to lose these 95 units of order. The customer will actually find a new supplier, and he will get these 95 units from there. Or maybe he will not even give the order of 5 units also for us, because he wants to give the bulk order at one time to one supplier instead of giving the order to two suppliers. Right? This is a big problem. So we need to reduce these kind of scenarios, right? The stock out and overstock. So in to reduce those scenarios, and we need to know them in advance. We don't want to know in a very short period of time, because if we know in advance, then only we can solve the problem. If we know in advance, because if we know at a very short period of time and customer is giving the order to us, we are again in a the bad position where we will not be able to serve the customer. So we need to find those scenarios in advance, so that we are able to reduce such scenarios of stock out because they are the high volume or maybe the high value items, which will give us a good business from the customer. So this is a business scenario, and this is how we're going to work on the business scenario. And we're going to use an algorithm called decision trees. So how decision trees functions, let's see that also. Decision trees. What are decision trees, right? So decision trees uses a metric, statistical metric, or let's say we say three metrics. One is called entropy, second is called information gain, and third we can say Gini index. So let's understand what is entropy, information gain, and Gini index. Okay. So if you are new to probability, then I just explained the concept of the concept of probability. Probability is applied when there is uncertainty in what is in the future outcomes. Probability is applied when there is uncertainty, huge uncertainty, or even little uncertainty in making the right decisions. There is This is a scenarios where we apply the probability. Means there is uncertainty or what is going to happen in the future. Suppose we have to make a decision, and the future is very uncertain, and then in that case we will say that we're going to apply the probability concept. Now, if you look at what is the concept of probability, if you look at the formula of the probability, suppose if there are a supplier, right? Supplier, okay, he is shipping your product. Let's say historically, right? In the order one, he has shipped product on time. For the order two, he shipped again on time. Order three, he shipped late, and order four, he shipped on time, right? So what is going to happen for the order five? Now, this is what we have to know this. So now we have already mentioned that probability is applied when there is uncertainty. So we don't know what is going to happen in the order number five because there is a uncertainty here. So when there is uncertainty, what we're going to do, we're going to apply the concept of probability. So the formula for probability is, suppose we want to know there are two outcomes here, right? There are two outcomes here. Outcomes, there is on time delivery or late delivery. Now we want to understand what is going to happen on the fifth delivery. We know what happened in the four deliveries historically. Now we are going to give supplier a new order five, and before giving the order, I want to know what is going to happen with my order, whether the order we will receive on time or we will receive late. That is what we want to understand, right? So the formula for the probability is, so we will find the probability of outcome on time. Okay. So now the formula for this is count of time, count of orders, count of orders where supplier delivered on time. Where supplier has delivered the order on time divided by count of orders delivered on time plus count of orders delivered. I'm writing short because this in short form because this is we have to cover this in very fast and we have to move to the main goal. That's why I'm covering this fast. So please bear with me. So out of in the previous four orders, how many times supplier has delivered on time? So this is three times, right? How many? And this is a numerator for which we are finding for the on time. What is denominator? Denominator, we have two terms over here. Count of orders which are delivered on time and the count of orders which are delivered late. So the on time which was delivered is on time is three, and the count of orders which were delivered late is only one single time. If you look at here, one single time. So this is one. So this is, if I mention this, 3 by 4, that is equal to 3 by 4 is some 0.75 or equal to 75%, right? Similarly, if I have to find the probability of outcome late, the formula is changing now. The numerator becomes count of orders where supplier delivered late divided by count of orders supplier was on time plus count of orders supplier was late, right? So this time supplier delivered late order is only one time. We have seen that. And the bottom is the denominator is 3 plus 1. That is equal to 1 by 4. That is equal to 0.25. That is equal to 25%. Right? So this is what we are. Uh, so the probability of on time plus probability of late. What is this value? Probability on time is 0.75 and probability of late is 0.25. If you add up both of them, it becomes 1.00. So when you add the two probabilities, means the probability of two outcomes, so the total probability is equal to 1, which is equal to 100%. Right? This is another equation which we have to take into consideration. So now we have seen how we want to find how we have to find the probability. Okay. Now let's move into the entropy side. Suppose I'm taking a box. In this box, we have four orders, right? Suppose there are four orders. Okay. And these are historically. We are looking at historically. So some order one was on time. Order two is also on time. I'll write short form OT. Order three is also on time. And order four is also on time. Okay. This is one of the box. And this is from the, let's say, supplier one. Let's go to supplier number two. Again, I'm giving four orders to order one is OT, order two is OT on time, order three is OT, and order four is late. And this is the performance of the supplier two. Let's go to supplier number three and let's look at the performance of supplier number three. Order one, order two, order three, and order four. So order one is on time, order two is on time, and order three is late, and order four is late. Okay, so now we have three suppliers and we have the performance of the three suppliers of their four orders historically. Okay, and we have just calculated what is the probability of. Now let's see, in the first case, what is the probability of on time, right? So there are four orders, 4 by 4. First order, the probability of on time is 4 by 4. Second is 4 by 4. Third is 4 by 4. Fourth is 4 by 4 because we have all the orders on time 4 and their total orders are 4. In the second case, there are three orders on time and one order is late. So here the probability of on time is 3 by 4. Probability of order is on time is 3 by 4. Probability of on time is 3 by 4 and probability of late is 1 by 4. Means out of 4 orders, 1 order is late. In other cases, out of 4 orders, the 3 are late. The fourth scenario, it will be out of 4 orders, 2 are on time. Out of 4 orders, 2 are on time. Out of 4 orders, 2 are late. Out of 4 orders, 2 are late. Right? In the first case, we know that whatever order which we have is completely on time. Right? In the second case, we know there is one order late. 3 orders are on time. In the third case, we are saying there are 2 orders on time and 2 orders late. So if you look at here, the randomness in this case is the randomness means is almost nil. Means because, why nil? Because all the orders are on time. None are late. If you look at this order, the randomness is increasing now because 3 orders are on time, 1 order is late. The randomness here is has increased. Now, if you look at the third order, the randomness has further increased. Means there are 2 orders on time, 3 orders late. So randomness has further increased, right? So the measure of randomness is called entropy. If you have gone to the physics and chemistry lessons in your school, you will see that the measure of randomness is called entropy. And that is what we're going to measure using the concept of probability. And so what we have to see is that the entropy means the entropy has to increase from supplier 1 to supplier 3, right? The entropy has to increase because here is completely non-random here. So the entropy is very less. Here the entropy is little going high, but here in the entropy is going very, very high because the randomness is increasing. So we have to devise a mathematical formula which will help us to figure out this entropy. Okay. So let's say in the first case, I have 4 by 4, right? 4 by 4, okay, into 4 by 4 into 4 by 4. What is this? 1 into 1 into 1 into 1. So this is 1. So if I multiply these probabilities of all of them together, I get 1. Second case, it is 3 by 4, 3 by 4, 3 by 4 into 1 by 4. Let's see how much we get over here. So if I multiply 0.75, I will use the power formula, power 0.75 to the times 4 times, right? 3 times. Then I'll multiply this with 0.25. This is coming around 0.105. Okay. Now we'll go to third one, that is 2 by 4. And if I calculate here, so this is power of 0.5 to the power 4, getting 0.0625. Okay. So what we got is the combined probability of the the first one is 4 by 4, 4 by 4, 4 by 4, 4 by 4. And the combined probability of the second case is 3 by 4 and 3 by 4 and 3 by 4 and 1 by 4. And the combined probability of the third case is 2 by 4, 2 by 4, 2 by 4. Right? Now, what I will do, instead of taking the product of this probability, I'll follow in another method which is called logarithmic approach. So, and instead of this product, we have done the product of logs, probabilities, right? Now I'll take the log of this. So log of 1 into log of 1 into log of 1 into log of 1, right? Now this is what? Log of 3 by 4 into log of 3 by 4 plus, sorry. This is, yeah, let me like this. Into log of 3 by 4 into log of 1 by 4. This is log of 2 by 4 into log of 2 by 4 into log of 2 by 4 into log of 2 by 4. So this becomes, and this is all to the base 2. So log of 1 to the base 2 is equal to 0 into 0. Or let's say if you can convert this into additive. So when you now log of A into log of B is equal to log of A plus log of B. So this will become log of 1 plus log of 1 plus log of 1 plus log of 1. So this becomes 0. Similarly, this is log of 3 by 4 plus log of 3 by 4 plus log of 3 by 4 into log of 1 by 4. This is log of 2 by 4. This is log of 2 by 4 plus log of 2 by 4 plus log of 2 by 4. So what we have to do now is that we have to take the average of these values, right? So average of this addition, this is 0. The average of these values. So log of 3 by 4, log of 3 by 4, let's measure that. So I will use log to the base. Log of 3 by 4 means log 0.75 to the base 2 plus log of uh, log of 0.75 to the base 2 plus log of to the 0.75 to the base 2, and the last one is log of 0.25 simply to the base 2, right? So we're getting minus 3.5. So this value we're getting minus, right? This value we need to get very minus. So what we have to do that we will convert this value into positive. For that, what we will do, we will put one minus sign outside the log. This becomes 3.245122, and this is a, now we have to do the average of this. So average means there are four values, so we'll divide it by 4. This comes around 0.81125, right? The first one is 0, second one is 0.825. The last one will again calculate this. So this becomes log of zero point 0.5 to the base 2, right? Plus log of 0.25 to the base 2 plus log of 0.25 to the base 2 plus log of 0.25 to the base 2. This comes around 0.7. Again, we'll put a minus sign outside because we want to convert this minus sign into positive sign. That will help us to estimate things properly, because we are more comfortable working with the positive signs than with the negative signs. And I have to do the average of this. So we're getting 1.75. So look at here the value of the entropies. So the highest entropy is at the last case, means value 1.75 is the highest in the last case, because we have the highest randomness in the performance of the supplier 3, the lowest randomness in the performance of supplier 1. That's why we got entropy is equal to 0. We got entropy is equal to 0 with supplier 1 performance, because there is no randomness there. So now what happened? We supplier 2 had only one late delivery, 3 on-time delivery. So the randomness has increased from 0 to 0.81. But in the third case, supplier 3 had two on-time deliveries and two late deliveries. The randomness further increased. That's why you got 1.75, right? So 1.75. So the highest randomness is present in the supplier 3 performance, because supplier 3 has two on-time deliveries and two late deliveries. Supplier 2 has three on-time deliveries, one late delivery, and supplier 1 has all the deliveries as on time. So there is no randomness present in the supplier 1 performance. So this is how we calculate the with the entropy. Entropy is a measure of randomness. If I generalize this formula, right? So what we have done is, suppose we had probability of A, right? So what we did, we had probability of A, and for example, let me say this is my scenario. Scenario is that supplier 3 scenario. This is on OT. First order is OT. Second order is OT. Third order is late, and fourth order is late. right? So how many orders are OT? So probability of OT, there are two orders are OT, right? Probability of late, how many orders are late? There are two orders, right? If I take if I take the log of this, so log of P of OT to the power 2, log of PL to the power 2, this becomes 2 into log of P of OT plus 2 into log of PL, right? Now this is our log, but this is not the average, right? This is sum. So what we need to find? We need to find the average. So average, there are how many orders are there? Four orders. So we'll divide this entire term by 4. So 2 into log of P of OT divided by 4 plus 2 into log 2 by 4 into log of PL, right? So this is what the formula which we have derived. And we are saying that we are going to take a negative of this, right? So to get a positive number. So what is the formula? If I say, if I write this P of T of M into P of L N, so what if this is a formula, then what is the generalized formula? The generalized formula is minus of M plus by M plus N into log of to the base 2 Pt plus N divided by M plus N into log of to the base 2 P of L. So this is called entropy's generalized formula. So you might have three outcomes, you might have four outcomes, you might have five outcomes, like we have on time, late, right? We might also have back order, right? If you have a stock out, then you might have a stock out and overstock. So this is a generalized formula for the entropy. Okay. Now we have to understand what is information gain. Information gain is, again, you have to find, there are two always when we are working with when we're working with decision trees or any kind of any particular algorithm in supply chain. When we're working with any algorithm supply chain, right? What we do is we work on dependent variable and independent variable. Okay, dependent variable and independent variable. So what is dependent variable? Dependent variable is what we're trying to predict, the outcome, right? The attribute outcome which the variable on for which the outcomes we are on which the outcomes we are predicting. Right? This is what we say. What dependent variable? Independent variables, the outcome which we use to predict, the outcomes which are the causes to the outcomes of the dependent variable. Okay. So what we do in the case of information gain is the entropy of the dependent variable, which we have just seen how we measure the entropy of independent variable, minus weighted the weighted average of the entropy of the independent variable, right? So this is called the information gain. So you have to measure the entropy of the dependent variable, and then you have to subtract it with the weighted average of the entropy of the dependent variable. So we know how to calculate the entropy. Just we need to actually do the weighted average of this entropy of the independent variable, right? Once we do this, I think we are going to